Or maybe in the meantime, if you have, sorry, yeah, in the meantime, if you have any queries, we can get started with your queries first before starting with week 4. So, any queries up until week 3, if you have.
Hello, sorry. I was a bit late today, so I even forgot the session.
Yeah, hi Nitin.
So, hello all. My name is Nitin. Hopefully, you have some question you post on forum, and I have answered you. So,
Yeah, there
hello.
are people are still joining, so maybe we can wait for another couple of
Oh
minutes.
yeah, yeah. Let me wait for a few minutes.
Yeah. Yeah, I guess we can get started. So,
Yeah, okay. Hello. Hi, my name is Nitin. Just give me a second. So, so please, if any of you have any technical doubt, any forum related doubt or question related doubt, please ask me here. So I will be here for a few 10 minutes. So please ask me, and my junior team will help you for solving doubt session. Or you have any question, you can ask him also. Oh, are you sure about choice of hypothesis function? Yeah, of course. Uh, I let me look into. Can you please post this question on forum? I'll look into and respond you on forum also. So, are you talking about question number? Mm, which question? Question 8, 9. Okay. Thank you. Okay. I'll discuss with professor and I'll let you know on forum. Please post on forum also in case you want prompt response. Yeah. Okay. Thank you. So I haven't checked the question. I'll check and respond you. Question number 5 or 6. Somebody asked in forum. Question number 6. Answers options are correct. Please look into little bit depth because that question actually the question very interesting. It required a lot of experience or a lot of thinking in terms of solving the problem. So think of something x1 x2. So there's a range of there's a linear regression I have been given. I guess 6,000 plus 1,500 x1 plus 2,500 x2 or something. We have asked very nice question. You can think about a bit and then fill the choice. We'll answer after the quiz will over, or we'll give the solution also. A very nice thing is there. So yeah. Any other question, please? If you have
Uh,
any, yeah, please.
Hello,
Yes,
myself Subhash Gupta.
yes,
Sir, regarding the question number 8 in assignment 4,
yes.
my I solved it and it work for two iteration.
Okay,
So in two iteration, it is giving the fourth option.
correct.
So now my question is, if we are considering the initial value weight that is 0, 0, and
Okay,
if we are taking it as a first iterations
okay,
and two more iterations, then we can get the fourth option.
okay.
So is it okay, sir?
Oh, it's fine. Let me check even the question. Just give me a second. Yeah, I got the PDF. So talking about question number, yeah, yeah, you can it asks you have to do three iterations. You can code in MATLAB and do three iterations. Even you do
Yeah,
with by
I did
hand.
code in Python. Then I
Okay.
found it is giving the for two iteration, it is giving the fourth option.
And what
And
about
other
the?
option are not coming in any number of iterations.
Okay, okay. It might be a typo or something. Please post this question on forum. I'll look into. See, these questions
One
are
more,
make of.
one more query, sir.
Yeah. Yeah.
About question number 9.
Okay.
About question number 9, it is giving for three iteration
Hmm.
option first.
Okay.
That
Three
case, if
iterations.
I am taking the three iteration, then it is giving the first option.
So
But
then
in
fine.
case of question number 8, if I am taking the two iteration, then it is giving the fourth option.
Okay. Okay. So it means there will be some issue or error, or even I'll look into this error and I'll respond you. It might be some error. What is the error in the prediction of the three? No, no. Have you calculated the error in the prediction, not just something else? Are you sure about it?
I have calculated the error, sir.
Okay, okay. Please post on this forum. I'll respond you. Or even next time I'll clarify in the next session, probably Monday. So it might be few of the question are created by other TAs also. There's a multiple TA for this course. We are, I mean, one. I'm a head TA for the course. Uh, I'll let you know.
Yes.
Okay, thanks. Thanks
Okay.
for point.
Welcome, sir. Welcome.
Any other? Uh, there's a few multiple errors in PPT also. I think one Durga has point out today. Uh, it might be a error in see, so this course has was been recorded in 2018 something. There's a multiple errors in week 5. There's error in back propagation in the video. I think 35-minute or something. In here in IIT Madras, we usually fix this error in each iterations. Like we are running the same ID 503 course we ran for last semester, and unfortunately in NPTEL we can't do because it's a rerun course. But if you found any errors, please point out on the forum. We'll clarify. We'll happy to clarify you. And sorry for inconvenience for the same. And any other question, any related question you can ask in the forum. I remember I was TA for last time also for medical image analysis course. You can ask as many as question you wanted. We'll happy to answer all the questions come from your side. Hopefully. Or any technical doubt, or even you want beyond the syllabus what we are not covering. See, this course is a basic course as per professor also have mentioned. It's a basic course. There are multiple courses are available in NPTEL or other also. But if you wish to explore a little bit more, you can do. There's no harm to do so and so. And if you want some question or something, and if you want somebody have point out some programming questions from our side, yeah, we have programming assignment also. So the course we also same course available here. So we have given 7 assignment, 7 to 8 assignment. The coding solutions in PyTorch as well as their video solutions recorded by me are available. If you wish, we can share with you also. But this is just extra material, not belong to this course at all. I mean, content of this course at all. And if you format about the exams, a few questions come about the format about the exams. So exam will be purely option basis or MCQ basis, and there will be no programming question also. So it's all about theoretical questions. So yeah, so we will share with you shortly, probably tonight. Yeah, Saran, I'll share with you. Please remind me on forum also. So yeah, any other question? Yeah, Saran, go ahead.
Sir, can we discuss about the question number 10 of assignment 4?
Yes, yes. Yeah, yeah, please.
So in graph, we have been given the graph between epoch and losses.
Yes, yes.
So almost in all these three graphs, similar kind of training loss and validation loss is
Correct,
showing.
correct, correct, correct.
So in my point of view, I think the fourth option is correct, sir. None of the above.
Based on these graphs, the scenario indicate model that has likely captured noise in the training data, leading to poor generation of validation data. No. So it asking about the gap. See, something underfitting, overfitting, or
Yes.
the similar concept. So you have when gap is much large. So it asking about respect to something. So I cannot answer here because since are graded questions, it's policy kind of things.
Yes, sir.
But
Yes.
can you please look into this thing? Different.
Uh, means that gap between the graphs.
Yeah, yeah, exactly.
Okay.
Which is
Okay.
the higher gap or something? It is a respective question.
Right, sir. Right. Thank you,
So
sir.
yes, yeah,
Thank
no, no issues. Uh, any other scenario I know? Once it comes to CNN week 6, we might be going week 6. The similar scenario happened. Something called uh, underfitting, overfitting. There's multiple vanishing gradient and exploding gradient and computational errors. Very similar finite line over there. So please distinguish both ideas very, very different. In RNN, Dr. Balaji have already discussed these three problems with CNNs, or that's why we go as deeper as in LX, VGG, and then resonate and densenet. Then resonate come with the idea of escape connections due to the exploding gradient or something. I think I might have asked a question similar in week 6 or 7, I think. So, uh, oh sorry, for you it will be week 4. For us it's week 6.
Yeah, so
Okay.
it's a little overhead, so we can cut this
Yeah, yeah,
here.
sorry. I'm little bit ahead with because we have to make questions 1 or 2 week ahead.
Yeah.
So okay, I think no questions. Thank you, Durga, and please ask any question you have with Durga. I think he's one of the. I mean, he can teach you well, and hopefully he's a expert in like kind of very good in the field. And one more thing. See, I am the product of this course only. So I did course in 2 year back, and I came joined IIT Madras, and so this is one of the course which is very close to my heart. I learned machine learning by this course only, so I have not done any other course and not found any other course are relevant this course. It's too good. I mean, we even I think
I share the same
Durga
with you.
knows
Yes,
Dr. Balaji, one of the best faculty. If you can see the expression, you can see the clarity of the mind he have. We don't have such faculties available here also. He's one of the best faculty I will ever say. Uh, Not in the India is like for me is the best. I don't find any substitute uh, for Balaji. So the way he will teach you, like he will drag and drop you somewhere in the second universe. And with the similar simple concept, it's not he will not pull you for jargons. He will pull you for the simple concepts. He's one of the best faculty. So I think you utilize these sessions and as much. And these all answers is scanned by Balaji also. So I am answering the question. I usually write answers and then ask professor to review it. So you cannot you can see the professor is also responding your query and taking each and every response, like whatever happening here, Dr. Balaji know, and he is scanning everything. So that is there. Like, we are thank to them for taking time and looking these things also. So yes, thank you so much. This is all from my side. If you have any question, please ask. Okay, thank you. I think no question. Please, Durga, go ahead.
Yeah, thanks.
And
Nitin.
sorry for interruption also.
Yeah, no issues. Thanks for coming. Okay, we'll get started with. Okay, now if there are no questions from the previous week, we'll get started with this week. This week, most of focus on linear regression. So we'll start with a problem on linear regression. So I hope you have already gone through the lecture videos. Okay, how do we formulate the problem here? So it is a straightforward problem. So to those of you who are not comfortable with programming, so I thought like it is always better to do some hand calculation first and then you try to implement it yourself instead of directly using some of the available packages. So what do we do here? So we have a model, have several of these data xi and yi. We'll follow the same notation as the professor uses. So y hat of I is essentially given by w0 plus w1 xi. And then we have our loss function. What is the loss function we have here? So before going further, so why are we using this particular loss function and why not anything else? So can I not use something like this? Whole cube. Why this and why not this?
Because in square the error cannot cancel out each other.
So if there are plus and minus, so in square they don't cancel each other.
Yes, sir.
So can I use power 4 then instead of 2? So instead of 3, sorry. So if I have a 3, then because there will be a plus minus thing and they'll get cancel each other, so we don't want that. So how about power 4? Can I use that? Or okay, like maybe that will be computation expensive, so you would say that you will not use power 4. Then can I use absolute value of this, something like this? Can I use this? This is ruled out because you told negative signs will, like errors will cancel off.
So in case of third, we will not be having the differentiability of this expression. Means we cannot find out the differentiation of this. In third,
Okay.
in case third.
Only at one point it won't be differentiable.
Yeah.
Okay, not continuous or maybe not differentiable, sorry. So with any higher powers, you would be saying that it is computationally more expensive, so we'll just stick with y square. Is that your answer?
Yes.
Or any other comments? Any other opinions on this or any other ideas on this? So this you would be saying like it's more computational or more expensive. There is even more mathematical basis for this. Why only to square and why not others? I'm not sure if you're already familiar with the concept, but we'll touch upon that a little later. Now we will stick with this. So okay, we came to the conclusion that we will use least squares. Now what do we do next is we have to minimize this cost function. So how do we minimize this? So j is my cost function. It's straightforward from here. So you have yi minus y hat is essentially w0. Sorry, I shouldn't have written it this way. Minus and then you try to minimize this. So by minimizing, like we have seen previously, when you have, this is an unconstrained optimization. So in order to get the minimum, you need to have del z with respect to w0 and with respect to w1, because they are the unknowns, or basically they are the parameters that I am varying to see which one of them fits better. So if I do this here, what is the first expression I will be getting? This is for this expression, and similarly for this. Now we have two equations, and then we have two unknowns w0, w1. If we solve them, then we will be getting this answer. So what is the equations here? So we have w times sigma I equal to 1 to 5. So this is one equation, and then the other one is I can solve these equations and I can directly get the answer. This is one way of going about. Alternatively, you can use gradient descent. In case of linear regression, the problem is straightforward, that you have just two equations, and then the difference, like they are very easy to differentiate. So you can directly get analytical expressions, and from them you just get two simultaneous equations, and you can solve them to finally get your answer. So this is straightforward in case of linear regression. But for more complicated objective functions, you would be using some generalized method like gradient descent. So how do you approach this in gradient descent is again straightforward. So I write w0. I'll use 1 on the superscript for the iteration number. Say a 10th iteration is w0 and minus 1. Some learning rate times. This is evaluated at w0 of n minus 1, so plus or minus here. So should I put a plus or a minus here? Minus. So idea is okay, it just comes directly from the name itself. So when you have gradient, essentially is like if this particular gradient is negative, it means if you go in that particular direction, if w0 decreases, then your loss function increase, or the other way around. So we want to ensure the loss function is decreasing, so we will go in a direction opposite to that of the gradient. So that's how we do this. Now we have an initial guess in this particular question. The initial guess is given to us, and we already have the gradient values here. So this is one gradient, or to put simply, so we have this as minus, I'm just taking out the factor out. 2 is just a factor that is a common one, so that kind of can get absorbed into the alpha. So this is yi minus yi hat, and similarly this is my del j minus, and similarly my del j del w1 will be so now you have these equations which can be substituted back, and when you solve, you will be able to get the answer. Now coming back to our original question. Okay, once you do this, you know, you'll get some model, like you have two equations at two unknowns. If you substitute all, you will get some answer for it. So you'll get some values for w0 and w1. Maybe can you solve these equations and tell me what the answer you get here? So if you are using gradient descent, you can use this as initial guess. Maybe like a couple of iterations will be sufficient. If you already have the code, then it is straightforward. If you are not using gradient descent, you can already you can right away use these equations, and from here you can directly get your W0, W1. So maybe I'll give you 2 minutes, a couple of minutes, or maybe 5 minutes. So can you tell me these answers that you get? There are some questions in the forum that I have seen that, that you did not understand how to actually differentiate this cost function. So that's why I just wanted to elaborate it a little here. So I hope it is clear now in this, for this function at least. Yeah, maybe you can solve and let me know the answers. And once you determine the values of W0 and W1, you can, like, it's just two equations, two unknowns, so you'll anyway get some answer, but we do not know if the actual system is following this particular process or not, this particular model or not. So then we need to somehow have a metric that tells us whether the model is perfect or not. One such metric is your good, like basically we call it the goodness of fit. Maybe one of you can explain it. So how do we measure that? There is something called R square. So how do we define R square? How do we calculate R square? So it is something by something. What is
1 minus is some squared error upon some squared root, some squared
of?
total, I guess.
There is something that is square. So what is it that is square on the numerator, and what is that is squared on the denominator? SSR and SST. Yeah, SSR and SST is fine. So you have y minus y bar, and then you have y minus y hat. So what are we trying to do here? So if you happen to see this earlier, if I do not know what is x and what is y, so basically I have some data x and some data y. As we discussed in probability, you can kind of think of this is coming from some, this is some random variable coming from some distribution p of x. Similarly, y is some random variable that is coming from some another distribution p of y. Now what we are saying, this can be any like it is a random variable, so it can be any value. Now given that I know that particular value for x, what is the probability for y? Can this be changed if there is a relation between x and y? Okay, maybe let me put the question, rephrase it slightly. So the probability of y given x, when is this true? When is this equation true? When they are independent. So basically only when they are independent you will have, yeah, only when they are independent you will have this equation to be true. So as long as there is a functional dependence between these two, then you will not be having both of them to be equal, which means by actually knowing the value of x, I would be able to better predict the value of y than without knowing the value of x. So what I am trying to say is, if you know the value of x, you will be able to better predict the value of y than without knowing it. Or this is something that we want to express it. So if we were able to do this, then we are good with our model. If our model is not able to do this, then it is of no use, because even if there is some relation that I am saying, but then even using that relation I was not able to explain the distribution of y, then there is no point in using that model. So this is something that is being written slightly differently here. So what we are trying to do is say, if usually, to those of you who are already familiar with I don't know if how many of you are already familiar with central limit theorem. So to those of you who have done probabilities, I hope you could recollect this central limit theorem. Even if not, the idea there is when you have several random variables that are being taken into account, say when you do take a measurement, then there are several errors that can add to it, and all the sum of the errors can be approximated with the Gaussian distribution. So if you do that, so what the takeaway from that is, you can essentially say if y is coming from a Gaussian distribution, So I'm just using this as my Gaussian distribution with some mean and some variance. And your x could also have the same phenomenon. Now if I assume, if I take all the data of y and then I calculate expected value of y, that is essential, that can be approximated as my mean. So that is your y bar that we are denoting in the denominator, and this yi minus y bar whole square is your SST, or basically your variance. So if I do not know anything about the x, then I can assume that y is coming from a Gaussian distribution with the mu, with the mean determined by y bar and variance determined by this equation. So that is what I would say if I do not know anything about the x. But now if I know the value of x and I somehow calculated this value of w0 and w1 with whatever method I choose, and then I calculate the variance with respect to model. So now there is a, previously the variance was with respect to the mean value, but now I have a model. So basically there are two models now, or two hypotheses. The first model is just y bar, so y hat is y bar. The second model is your whatever we have done now. So with the first model, just with an average, I was able to explain the entire data itself. In the second model, I have a little bit more complicated. So by doing this particular modification, how much of the variance within the data am I able to reduce? That is the whole thing that is being captured in this R square term. So by using the model y bar versus using y hat, how much of the variance that I could have decreased? If the R square value is close to 1, then you have a better fit. If it is otherwise, then it's not going to be a better one. And y exactly square, maybe it's not the right time, maybe we'll introduce that a little later. Just to give you a brief idea, is it because of the ridge and the lasso regularization? No, regularization comes a little later. Not really because of regularization, it has nothing to do with regularization. So if you happen to see that most of it is coming, like I'm assuming this Gaussian, so if you can recollect what is the PDF for a Gaussian distribution? So if x is my random variable, what is the PDF of Gaussian distribution? It goes something like exponential of this. So what we are trying to do here is we are trying to maximize this probability of y given x. This is something that will come out to be this. So if you want to maximize this, so as I told before, what you want to do is, without knowing x versus knowing the x, there should be some difference, and by knowing x I should be able to better predict the value of y. That is mathematically shown by actually maximizing the probability of y given your x. Now as if you want to maximize this, and this is my distribution for like this is a Gaussian distribution. So if you happen to see here, there is a minus here, which means I can only, what I can do is minimize this particular value, where mu is essentially the model that you will come up with. Or in case of here, instead of x, like the probability is with respect to y, so your variable will be exponential of minus y, minus mu is your whatever model you are using, y minus y hat by whatever variance you have. So maximizing this is equivalent to minimizing this particular quantity. Since you have a negative sign here, and like if this particular quantity increases, then exponential as the value goes to infinite, exponential goes to 0, so your probability will become 0. So what you have to do is try to minimize this, then the exponential value will increase and your probability will increase. So maximizing this probability is equivalent to minimizing this particular function, and that's how you ended up with taking your objective function as your least square instead of cube or power 4 or anything else. Is that clear? Yes, thank you. So were you able to get the values of W0 and W1? So that will be close to 2 and 3 or something, 1.8, and maybe you can try it. It will be close to 1.8 and 2.9 or something. So 2 and 3 are the actual values you will be getting. Okay, so what would be the value of this probability of x comma y? So now it should be straightforward. So it will be probability of y given x times probability of x. Can I comment anything on the probability of x? Like I told you now, the probability of y given x is basically what we want to do is, after knowing the value of x, y should be, any errors in y should be completely Gaussian distribution. So this will be a Gaussian distribution. So what about probability of x? Can I comment anything on the probability of x? So this is basically by input. So usually I cannot comment on this. It could be anything. This is the only one that I can comment, given some model or probability of y given x, as well as your w0 and w1 is something that I can comment on, and this is something that I want to maximize. So that's with the question 1. Yeah. Now we'll get back to question 2. It's a very simple question, but however I just want to ensure that you are familiar, whatever is being taught in all 5 gradient descent methods, you should be familiar with that. So just take a simple problem and we'll try to do one iteration or maybe couple of iterations, then you will understand the working of it, and then whoever is comfortable with programming can try to program it themselves and then compare the results with any of the existing modules that you have. So standard is a gradient descent. So gradient descent is, by now you should have been familiar with it. So how do you start with it? My cost function is, or objective function is y equal to x square. So, and I need to find the value of x, or to put it, I will say argmin of y, or essentially what is the x minimum. So if I want to implement it, what will be the pseudocode for this? For this particular case, you start with an initial guess x0. Like I'm just denoting whatever subscript here is your iteration number. So how will I get x1 from x0? I should be going in the opposite direction. So minus some learning rate times dy dx calculated at x0. So this will be, in this case, dy dx is 2x. So if we do another iteration, so what will be the value of x2? x1 minus alpha times. So gradient descent is straightforward, I guess. Are there any queries in gradient descent itself? The normal gradient descent without other alterations. So this is 1 minus 2 alpha times x1. So if you just keep doing, so this will become, if you substitute x1 here, so it will be 1 minus 2 alpha square times x0, and so on. After n iterations, this will essentially become x0 times 1 minus 2 alpha power n. So whatever alpha you choose, as n tends to infinite, your xn will eventually go to 0 for if alpha is actually chosen between 0 to 1. So this is clear. So why do we have to use momentum? So if gradient descent is fine, so why did we go to momentum? So why, what is the reason that made us go to momentum method from gradient descent, from the steepest gradient descent? Did you see any problem in this method that actually made people think that this method is not sufficient and they should come up with other alternatives? Large running rate. Actually didn't get it. So you mean to say I should use large running rate can cause issue of oscillations? A large running rate can cause issue of oscillations. Okay, if you consider this particular problem here, for this problem that that we are talking, y equal to x square. So if I increase the value of alpha, do you think an oscillation will occur here? Okay, so here if alpha is less than 0.5 versus alpha greater than 0.5, there are two scenarios. If alpha is less than 0.5, you wouldn't have anything. Like if you see here, if alpha is less than 0.5, then 1 minus 2 alpha will be positive. So this will be some positive quantity less than 1. So if your n is increasing, this will keep on decreasing, and then it goes to 0. So this is the fine scenario. Now if alpha is greater than 0.5, or essential alpha greater than 1 by 2, then 1 minus 2 alpha will be negative. So you would see what happens is xn is x naught times some negative quantity power n. So if your n is n is an even integer, then you will have a positive value, and then you have an odd integer, it will go to a negative value. So it will keep on oscillating between positive, negative, and positive, negative. That is what he was referring to. So for larger running rates, if alpha is less than 0.5, in this case that is the smaller running rate. So this is the maximum running rate you can go to. So you would eventually slowly come step by step, and then you eventually reach your minima. But if this is for alpha less than 0.5, so when you have a larger learning rate, initially you start with say some positive value, and then for the second one you might be here, and when the third one comes x for 3, since this quantity is negative here, you would go to the other side of it. So you would come on the other side, and then you would come here. So this would keep happening, and then eventually you will come here. Instead of coming in the straightforward way like this, you will be oscillating around your minima. Okay. So I think this is what he was trying to say. Eventually it will converge. Yes, it will oscillate, and finally it will converge. So how exactly did we overcome this problem using momentum method? It's like, does momentum method solve this problem? Does it reduce oscillation? Or can I not comment anything like that? Yes, it will reduce oscillations. Okay, I have one answer saying that it will reduce oscillation. Anyone who says otherwise? So okay, why do you think that it will reduce oscillations? Or what are some of the characteristics that you need to know that whether the oscillations will be there or not? Learning rate. Okay, learning rate. If it is too high, there will be oscillation. If it is too low, there will be like you will eventually converge. But the problem that we have right now is we do not know what learning rate I should be using. For this simple problem, it was quite easy. You could know that if I use alpha less than 0.5, I will actually directly converge without any oscillations. Because the problem is simple and you can actually do it analytically, so you were able to find the right value of alpha. But in real scenario, when you have too many parameters and your objective function is a little bit more complicated, you would not be able to calculate this alpha directly. So you would not know what is actual learning rate you should be using. Then how would you solve that problem? Like, is this problem exactly solved in your momentum method? Even in momentum method, so okay, how do I do xn in momentum method? How do I get the next value of the particular parameter in momentum method? It essentially has two terms. One of them should be very similar to what we have in steepest descent. So you have minus alpha times dy dx at xn minus 1, or let's just write x1 and x0, or xn minus 1, or maybe we'll use a little bit. At next step should be given by whatever is the current step, and then you also have something else here. You have something like gamma times xn minus 1, and then from this you will add whatever the current value is. This is how you will be updating in momentum method. So you have three terms. This is like whatever is the current value plus some correction term. That is a step that you are taking. That step depends not only on the gradient, it also depends on something else. So by seeing this expression, you still have, now previously I just have one parameter alpha that I have to vary, but now I have one more parameter gamma that is also an unknown to me. So do you think this will solve the oscillation problem? Like previously I don't know how to find alpha, or basically the learning rate. Even now I have alpha. So does momentum method offer me anything to calculate alpha explicitly or something? So how do you think it will solve my problem? So the idea for the momentum method is just like to get initially the problem was, if you happen to see the steepest gradient descent, what we have is I will just write a little slightly different way. So x minus alpha times, this is what we have in steepest gradient descent. So if I just take it to the LHS and write this as delta x for n plus 1 step, is given by minus alpha times dy ds at xn. So what we are saying is at every point xn, the step that we have to take is proportional to your gradient. So if your gradient keeps on decreasing, the step size will keep on decreasing. So when you have y equal to x square, so something like this, like for x less than 0, if you are at this point, you have a little higher value of gradient. As you come closer to 0, your gradient keeps on decreasing, so your step size will also get decreasing. So initially from here you jump to here, but then because your gradient has decreased, now you will jump to 3. Even further if you go, the points will become closer and closer. So as you go closer to your solution, or then your step size will gradually reduce. Say suppose if you have some function like this, or you can even take your tan x function. Most of them will have some like as you go closer and closer towards your minima, you will actually have your gradient decreasing. So your step size will keep on decreasing, and then it will take more and more times to actually reach there. So you should be actually, as and when you get closer to your solution, you should actually be increasing your alpha a little bit to overcome this reduction in your gradient. But what if you do not know that beforehand? So somehow you need an information of the gradient that was there before. Whatever step size I have taken before has to be somehow incorporated into this, so that you would not actually be slowing down here. This is the idea is very similar to what you have. I don't know how many of you are from. There are some people who told they are from aerospace, and there are some mechanical. So this, or who are already familiar with, everyone is familiar with Newton laws. So if you have something called inertia, so you tend to continue in the same direction. So you won't get stuck here. So if you start from some point on the top, what happens is you gradually change your step size. But what we are saying now is, don't change your step size just because your gradient is small. You also consider that whatever is the step size that you have taken before, take a weighted average of these two. The step size whatever I have before is xn minus 1 versus the gradient step that I have to take. I am taking a weighted average of these two. So alpha is for the gradient, as well as this gamma is for the previous time step. So this is what we are calling momentum. If you have some momentum, you will keep going in the same direction. Basically, if you have some inertia, you will keep going in the same direction. And this will be your external force kind of stuff. So with this, the next time step will be a weight combination of the previous time step and your so I just want to highlight this a little here. So in the slides, I think he told that, so they will be correcting this. So in the lecture videos, you might be seeing a plus here. So just don't get confused with that. So this is minus alpha times dy dx at xn, or to put it in the format of lecture videos, we always need a minus. The minus sign is actually missing in the presentations. That is being shared with you in the portal, that he will be changing a little later. So just be careful with that. So as long as you are sure that delta x, that the step size that you are taking should be in a direction opposite to your gradient, only then you will be minimizing your objective function. If you are going in the direction of gradient, if this is a plus, then if your dy dx increase, then your delta x will increase, which is something that you don't want. I mean, your direction shouldn't be in the way that your objective function is increasing, it should be opposite to that of. So we need to put a minus here. So just ensure that you do this. This is a correction that he'll do a little later. And coming back to here, so what is the gamma value? Like it is usually you can vary this, but the usual value is 0.9. So is the idea clear? So what we do in momentum method is, only if your gradient is too low, when gradient value is too low, then you should not take small steps and be stuck there. Instead, you actually, if you put this momentum, then it will actually skip that, and then it if the previous gradient was too large, it will have sufficient to say, if you the example that is often cited is, you have a ball coming down like this. Now if you have a steep slope here, do you think it will stop here, or it will just go off? if it is coming like this, since the ball has some velocity, it won't just stop just because gradient is 0. It will keep continuing with the same velocity and it will pass this point and it will go even lower. That is what is expected. But however, gradient descent doesn't take this velocity into account, or to say the momentum into account. If gradient becomes 0, then it will just stop there. The ball will stop there, which is not physical. So you need to incorporate this momentum component into it. But as you said, if you have momentum, say now I have a domain something like this. Because of momentum, even if I reach a point where gradient is 0, because of the velocity that it already has, the ball will just go to the top. The ball will just go to the top and then it will slide back. And then these oscillations will keep going on, and eventually you will come to the solution. So by using this momentum method, your oscillations can actually increase instead of decrease. So initially one of you have actually answered that your momentum method will actually decrease oscillations, but you can see that oscillations will actually increase in case of when you use momentum method. Is the intuition clear why the oscillations will increase? Because you have the velocity, like you are coming with some velocity. If there is a minimum, you just won't stop there because you already have some velocity. You will go beyond that point. Only when you have sufficiently, the gradient is sufficient enough to pull you back, you will come back again. But because you already have a velocity, again, it's like a spring that you will oscillate and eventually come to your minimal point. Is that clear? I hope it is clear. Okay, then so I'm just going through this because there are some corrections in the slides and I don't know when it will be uploaded, so I just want to write the expressions for you so you will be able to understand it, like there won't be any confusions in this. This is with respect to momentum method. So now you know that there are some oscillations in this momentum method, so how can I reduce this number of oscillations? That where your NGA comes, NAG comes, Nesterov accelerated gradient method. So what do we do here? So what is the primary reason that we are having oscillations in momentum method? In steepest gradient descent, the reason for that oscillations is your learning rate, which is something that we did not address as of now. We will address a little later. But we know that if your gradient is too small, then we will not be able to converge faster. So we need to introduce momentum into it. But if we introduce momentum, your oscillations are increased. So what do we do now? What NAG does is it will have the momentum term as it is, but then the gradient term, when you have this gradient term, it will calculate it slightly differently. So instead of taking it xn, it will calculate at some x star. So basically, if this is your xn, because of momentum, you would actually be going to some x star, and then you go there and then you see if the gradient is actually in the correct direction or not. If it is in the correct direction, you will stay there. If it is not, then you will reduce your point and then you will come here. So this will be your xn plus 1. So if you are directly using the momentum, you would be here x star, and from x star you would come back to somewhere here. So if it is pure momentum method, so what would be happening is this would be your xn plus 1. So from here you directly jump here, and from here you will oscillate here, from here you will go here, and then this is what will be happening in a momentum method. But now what we are doing here is, instead of actually doing all these oscillations, I will calculate the gradient here and see if it is in the right direction. What is the right direction in this case? So how do I know that? How do I calculate this gradient? So what is this x star? X star is basically the one that I would be going if I am following with the momentum method. So what is that? So if I were following the momentum method, so it's like delta xn is your local minima. No, sorry, x star is not local minima. Okay, maybe I should use a different notation. So I'll just put xn star or xn plus 1 star. So what is this xn plus 1 star is, ideally I am at xn and I want to go to the next point, but if I am using the momentum method, I know that it might cause some oscillations, but what we don't want to do is, okay, we will try the momentum method, but then we won't directly go there. We will calculate the gradient at that whatever point that it would be going if it were following momentum method. So basically, if it follows momentum method, it will go to xn plus 1 star, and then we will calculate the gradient at xn plus 1 star. So xn plus 1 star is xn plus gamma times delta xn. How do I get delta xn? I already know what is my current value, and I know what are the parameter values one step before. So from this I will calculate xn minus 1. So this is basically the step size I have taken one iteration before from the previous iteration. That plus whatever is the current value will give me xn plus star. So if there is no gradient term, this is where I should be. Now using this point I will calculate the gradient and see if my gradient is actually positive or negative. If the gradient is positive, then I should reduce my direction. Maybe I will, a small graph can help explain this better. So in our case, the function is something like this, y equal to x square. So all I am saying is, you started with some point, you have taken some step size. So this is my initial point. So I came to say 1, 2 here. So now at point 2, for a given learning rate and for whatever momentum parameter I have chosen, I can actually end up at some point like this. If I just use this expression, xn plus 1 star is xn plus gamma delta xn. Now at this point, if I calculate the slope, is this positive or negative? So previously the slope was negative. So at this point the slope is actually positive. So what I will do is, if the slope is positive, instead of going here, instead of going like this, I'll actually reduce it a little bit. So that is what this minus sign will do here. So it will reduce the slope a little bit. So you'll actually come here. So this will be my 0.3 and this is 3 star, or x3 star and x3. So if I was at 3, then I would have more oscillations compared to, so if I was following the 3 path, then I would eventually come here, here and so on, which is something that we are avoiding by actually coming to 3 directly. So when now we are at this 3, then eventually it come here and it will converge here, instead of actually following all this path. Is this clear, or are there any queries? Even this, there is a slight change in the sign in the slides. There needs to be a minus here, and then you have to use this particular term over here. So basically, if you got gradient positive at x star, then we had overstep, exactly. So you have to reduce your delta x. That's why there is a minus here, correct. So if the gradient is negative, then you are going in the right direction, so you don't have to worry much. Yes, you are going in the right direction, so you can actually increase it a little bit. So minus minus gets positive, so your step size will increase. Which optimization converges fast? The expected one is this NAG works faster than your normal momentum based methods. Like basically your oscillations will actually get reduced, so it will converge faster. Now if you were to ask me steepest gradient descent versus momentum method, it's like if you compare the momentum with, sorry, I think I changed the color. Momentum versus NAG, this is fine. Now what happens momentum versus SCD? What do you think will happen? Which of these two do you think will be faster? So okay, you are saying SCD will be faster. It is actually a little bit more complicated than that. Like just like he pointed out initially, in steepest gradient descent, your learning rate has a very important effect. Even though momentum method, what you are doing, your step size is actually much bigger than your. If you compare the step size for momentum based and steepest gradient descent, the step size will be much larger in momentum based methods. So basically, you are adding another term here. So you are adding this term over here. because of this term your step size will be much bigger than your, this is your steepest gradient descent step size. This is the additional term that you are adding in case of momentum. So the step size will be much bigger in case of momentum 1. So it can actually converge faster. However, it's like a bit late trade-off. Now because you are taking bigger time steps, it can oscillate, and because of oscillations it can actually become slow. So for some objective functions it might perform better, and for some others it might not perform better. So that depends again on your objective function. So we cannot say right away that which one of them is actually better than other. So sometimes one is better and sometimes other one is better. It's just because of this trade-off that you are having here, that any one of the term can dominate at some points. Okay, now this is clear. So I hope this is clear. So what we have now, the next method, before going to the next method. So here we know that the oscillations are a bit reduced than momentum method, but still the original problem remains. The oscillations are there if your learning rate is not properly chosen. So somehow we need to have an adaptive learning rate. That is what the next two methods will discuss about, ADA grad and ADA delta. So what we want here is we need the learning rate to be changing, but how do I change my learning rate is the question. So I want alpha to be changing with iteration number, or maybe I'll write this alpha as some function of iteration number. But what function should I be using? As your iteration number increases, so if n is my iteration number, if your iteration number is increasing, then your alpha should decrease. Will this be sufficient? So if I have something like this, can I write a function like this? Xn plus 1, or basically your delta xn is your step size, is minus alpha by n times, in our case, dy dx at xn. Can I write it this way? So I will take alpha to be a very high value initially, say 1 or something. But then what happens, as your iteration number increases, alpha will become low and low, and you will not actually get any oscillations. So is this fine? Can I write it this way? It's not ADA grad I'm saying, so this might work in this particular case, that y equal to x square function, it might work. You can actually have other values like y only 1 by n, you can use 1 by n square. You can use any different other combinations, and you can come up whatever rate you want. That is something that you need to experiment with your objective function. What ADA grad tells you is, say if I have multiple variables, multiple parameters, then not all of them will have same rate of learning. The same learning rate for all of them could be working. So some might be having lower values and some might be having higher values. That is when you have to actually have something that is different for different parameters. That is point number 1. One is that different parameters can have different learning rates. Second one, I need to change alpha with iteration numbers, but if you see, what if in this particular scenario, even though your ideally what we want is our objective function should actually reach a minima, in that scenario dy dx should be 0. But now you introduce something like this, which could have happened that even without actually reaching the second term to be 0, the first term could actually go to 0 after a certain number of iterations without the second term being 0. In that scenario, your delta x becomes 0, and because of your whatever stopping criteria you keep, this will actually stop after a certain point. There is no point in doing further iterations. That could also happen, right? So if any one of these terms on the right hand side becomes 0, then your iteration will stop. So when I am doing this, whatever weightage that I am taking for this learning rate, I need to ensure that I am also taking into account the fact like the actual gradient values that are coming up. So what you want is, say if I've just plot something like this is my gradient value at some iteration step versus number of iterations. So what you would expect is, if initially your gradients will be too high, eventually they will converge and finally they become 0. That is what we expect. And when the gradient becomes 0 is when you have identified your optimal rate, and as and when you get close to this particular values, you should actually reduce your alpha. So instead of doing with respect to number of iterations, you should, if instead you are doing with the actual gradient value itself. That is something that we do in AdaGrad. So what they do here is this weightage factor that we are calling here, they will be doing summation of whatever previous gradients that you have calculated for that particular variable. So I will just use a notation that the professor is using. So he was using a notation called Gn is for the gradient, and then he was using capital Gn to represent summation. I'm just removing the index here. So he was actually writing Gni. I'm removing that because for this particular problem that we are discussing here, it's just a single parameter. So you don't have a parameter index. So I'm just removing that index. So it will be easier to understand with one, and then you can extend it to others as well. So for any one index is what I am writing. So you will have Gn square, or I'll write Gi square, where I is from 1 to n. Basically from the first iteration to whatever is the current iteration, I keep on adding these things. Then I'll have the total gradient, and then I'll take a weighted average of this one. Again, to correct this one, so you have delta x plus 1 is actually minus alpha by, this is just to be consistent with the units, you have taken square root of Gn. It can so happen that your gradient can become 0. This is something that is often done when you write the course, is you always add a little epsilon here to whenever you are having some fractions in the denominator, to ensure that you won't actually get infinities or any not nans. You just put a small value, say some number close to like 10 power 6, 10 power minus 7, sorry 10 power minus 6, 10 power minus 7, or some small value to ensure that this term doesn't go to 0, times your whatever gradient that you have. This minus is not there in the slide, so the same thing that goes everywhere. So just ensure that you take care of this minus sign appropriately. Yeah, as the problem still remains the same, that if your number of iterations keeps on increasing, your gradients will keep on accumulating, and then your denominator will keep on increasing, and eventually, even before this particular gradient becomes 0, this term on the left, the first term can become 0, and then your update can become 0, which is something that we don't want again. So that's when your next step comes, in which what they do is, instead of taking summation, they'll just take an average. So your sum might keep on increasing, but your average won't increase that high. So that could actually be a much better way of changing your learning rate, like better way of having an adaptable learning rate than the current one. So instead of this, we'll be using some other function. So idea is to use some functional form of whatever gradients I have before times the present gradient. This function you can vary. In AdaGrad, you are using summation. In AdaDelta, you are using a mean value or expected value. I'll just write average, running average. So this way we ensure that as the number of iteration increases and your gradients keep on reducing, this value will kind of, this denominator will keep on increasing, so this entire term will actually get reduced. So if you go with further number of iterations, your learning rate will gradually reduce, so you don't have to worry about actually varying it. So even initially you can start with a very high learning rate, but if you are close to the solution, your learning rate will become 0 or close to 0, so that you will actually converge much better than using the steepest gradient descent. The main advantage comes when you have multiple variables, multiple parameters, which is something that I didn't have here. But if you have multiple variables, then each variable can have different suitable learning rates. That is when this actually has some benefit for it. Maybe we'll take one example in the next problem. But before going there, so is this clear, or are there any queries in this? Yeah, I think it is clear. Maybe before actually going to the next problem, you can actually test this out yourself. How many of you are already familiar with Python or any other language that you are familiar with? If you are using any of the libraries, if the course is discussing, say PyTorch or TensorFlow or even sklearn and scikit, all these are inbuilt into them, so you don't have to code it yourself. You can vary these parameters like your alpha, that is your learning rate, or momentum parameter, and see how it oscillates and stuff like that. You can experiment it out yourself. The reference code is already provided in the course web page using scikit. You can even use that code. Yeah, we are 1 hour into the class, so I'll just wait for 5 minutes. So if you have any queries, you can ask me. Like, if everything is clear till now, then maybe you can try solving this problem. It's one step further from what we discussed. So till now what we are doing is we have an objective function which is a scalar. It's always some finite quantity. So even when you have 100 data points, what we are doing is you're just taking sum of it or average of it and somehow bringing it to one number. So what if you have a vector? Your objective function is a vector and your variable is also a vector, input is also a vector. So what do you do? Can you implement gradient descent with this? If you want to implement, how would you go about doing it? So first of all, do I get this kind of scenarios in real world? Like, do I have objective functions which are vectors? You do derivative, okay. Okay, for this problem, if you were to do, what would be the derivative? So say if I want to, like, it is clear, you want to minimize this f of u. So you should put df du equal to 0. Till here it is clear. So how do you do this? Df du. What is the value of df du in this case? So should I put del f del x, that's what you are saying, equal to 0, and del f del y equal to 0. Okay, if we go with this, so what is del f del x? F is a vector, so if you want to do with it, it will be -1 and 2x. It's like I'm doing derivative of a vector with a scalar, so you'll be getting a vector. Or if you want to write it directly in this, when you do like this, we have discussed when we are discussing linear algebra, if you have a vector that you want to do a derivative with another vector, you would be getting a matrix. That is essentially this. So you will have a matrix something like this. We have a name for this. I'm just writing J. That is your Jacobian. To those of you who are already using TensorFlow, if you are using TensorFlow, you might be aware of two different functions. So if you are using gradient tapes, you have a gradient function and a Jacobian function. These two are two different functions. This will always give you a vector. Even if it is, even if you do a vector derivative with a vector, it will turn out to be a vector if you use this particular function. If you actually want to get this matrix, you have to use the Jacobian function. So okay, say I got the Jacobian function. So what do I do next? So like if you follow with the standard notation that we are following, we need to get the step size. So I'll say the step size delta u, say n plus 1, is minus some alpha times whatever Jacobian I have. If I write it in this way, what should be my alpha here? So this is going to be a 2 by 1 matrix. 2 rows 1 column, and then this is a 2 by 2 matrix. So what should be my alpha? Should be a 1 by 2 matrix. So what should be this alpha now? So like till now we have just one learning rate, but now we are having 2 learning rates. But before actually solving this problem, maybe I should ask a more fundamental question. So can we have this scenario? Can you give an example where you have your objective function as a vector instead of a scalar? No idea? Okay, fine. Yeah, that is also fine. So this is something that you usually don't encounter. This is something called multi-objective optimization, if you are already familiar with it. Where you will be having two different objectives. So I've just put it as a vector. So scenarios are like, if you are in, say if you are in a manufacturing or in an assembly line, you might be wanting two different objectives. You want to reduce the total time, that the process time, or you want to reduce the total time from the beginning of the process to till the finished product is obtained, and at the same time you also want to ensure the quality is within certain limits. So if you try to minimize this time, what happens is your quality can actually get deteriorated. So our objective is to reduce the time, at the same time increase the quality, but both of them are kind of interlinked to each other. So if you try to reduce this one, the quality will also reduce, so I will not be able to solve both of them directly. So this might seem trivial to you, that doing del f del u equal to 0 will actually give you solution, but it might not actually converge, because if you try to reduce, like you can see it here directly in the function, if I try to reduce the first function, I have to go to 0, but then I do not have any control over what the second function does. In this case, say if you want to minimize x square plus y square, you would be going to 0 0, that is your best case. But if you go to 0 0, your minus x is not minimum. Say if you use x equal to 1 or so, then x square plus y square will be 1, will actually be much higher than the global minima that you have. But the other one, minus x is actually minus 1, which is lower than the minima that you have for 0 0. So if I have two alternatives, I can use 0 0. Hope I made it clear. Are there any questions in this xy? I can have two functions, f1 as minus x and f2 as x square plus y square. So if I have 0 0, then I can have something like this. If I have 1 0, so if I try to reduce one function, then the other function will actually keep on increasing, and this keeps going on. So I wouldn't be actually able to directly come to a solution in this particular way. So the problem is not actually completely defined, but this is something that you might encounter as well. You might have some gradients that you want to find for vectors as well. So what you would be doing in those scenarios is you kind of come up with a new objective function. It's like you can convert this vector function into a scalar function. Depending on you have to add additional information to do that. Say in this case, say for the example that I have told, you want to minimize your time, at the same time you want to increase your quality. So your objective function now, instead of writing as a vector like this, which is something that you will not be able to solve, you will pose this problem as some alpha 1 plus alpha 2, or these are some weights that you are taking. Since I want to maximize the quality, I am writing a minus, so that minimizing the negative quantity of quality will actually increase it. So if you write in this way, and this alpha 1 and alpha 2 are something that you can vary depending on your particular scenario. Say for some products, quality is more important, but some products the time in which you deliver are more important. Depending on this, you vary these particular weights. Then you will have a scalar function, and using that scalar function you can directly solve with whatever existing methods that we were discussing. Is this clear? Yes. So now we can take some value here. Say let me take, I'll just take alpha 1 and alpha 2. So now I'll formulate my new objective function f of xy. Alpha 1 times minus x and alpha 2 times x square plus y square. Now with this, everything is straightforward. So all you have to do is del f del x equal to 0. That will give you minus alpha 1 plus 2 alpha 2x. How to get alpha? Yeah, as I said, alpha is something that depends on your application. So in this case I did not tell you how I got minus x and x square plus y square. So alpha is some arbitrary number. But in some real world problem, something like the one I told, so you want to minimize time and quality. Sometimes there are some products for which delivery line is much more important, or to say if you did not deliver a product on time, then the loss you incur would be much higher than delivering products on time with lower quality. Say you can take the total cost, you have something called opportunity cost or whatever. I do not know the name of it exactly, but you have something called, there are some things they use. You have cost that will tell you incur for actually delivering low quality products. And you also have some cost that will tell you what happens if you have late delivery. The cost that you will incur if you deliver it late versus the cost that you will incur if you deliver low quality products. If you have something like this, then you can actually take a weighted average of this. So essentially to say this is C time and this is C quality. So this alpha 1 can be taken as and alpha 2 will be 1 minus alpha 1. This is for this particular application. For other applications it might be different. It is kind of even other ways are, there are people who actually do it on slightly different way. So what they do instead is they actually try with different possible combinations of alpha 1 and alpha 2 and then come up with something called, I don't know if you are familiar with it, a Pareto chart, a Pareto front to say more precise. So what they do is they try with different values, different combinations of alpha 1 and alpha 2. So alpha 2 is essentially 1 minus alpha 1. So I will just vary alpha 1. So I will take 0, 0.1 and so on till 1.0. And then for each of these possible combinations, I will say I have different values, different alternative values. And each of these I will calculate what is the cost I will incur or whatever new objective function that I have. And from there I'll have to, like, all of them are equally likely from whatever information I have given in the question. From this question, I cannot say what the alpha will be. Any of these combinations is actually a solution for this particular problem. So which one of them to take is decision that you have to take. You, in the sense that whoever is the end user has to take. As a modeler, this is something that you do not have any idea about. That is something that you cannot comment on this. Even if you try to solve from this particular, if you try to solve using your previous method, so even if I put del f del x equal to 0, that wouldn't give me, it will give me two equations, but then I will not be able to solve x and y. So if these are my equations, I can take y equal to 0 and x is alpha 1 by 2 alpha 2. So by actually varying alpha 1 and alpha 2, you get different values of x. Gradient descent is Jacobian. I didn't get your question. So gradient descent is not Jacobian. See, the idea of gradient descent is you should be moving your weights or whatever your parameters are in a direction that will reduce your cost function. And in order to get that direction, we are using the gradient information. If your cost function is a scalar, then the gradient is going to be a vector, or like if you have single variable, it will be a scalar. If you have a vector, it is going to be a vector. If your objective function itself is a vector, derivative of a vector with respect to another vector is going to give you a matrix. In this particular problem, since I have given my objective function as a vector, the Jacobian turned out to be a matrix. Is that the question you are asking or something else?
Sir, I am asking what is gradient descent for the problem.
Yeah, so this is it. So you have here, right, delta un.
Okay, this alpha 1 minus x. Oh, that one. Okay.
Yeah. So this alpha is your essentially now alpha 1 and alpha 2 that you have
Okay,
to
sir.
choose.
Okay. Thank you.
Yeah, now you have y equal to, so the solution is essentially y equal to 0 and x equal to alpha 1 by 2 alpha 2. By varying alpha 1 and alpha 2, you will get different x, and you do not know which one of is better directly. So this is the solution that you have here. So any other queries in this? difference between Hessian and Jacobian. Trial and error. Okay. I didn't get your comment. What do you mean by trial and error? Okay, how do you get alpha 1 and alpha 2 is by trial and error is what you are suggesting? Okay. It's a bit of trial and error, but still it's like depends on your application as well. If your application, it's like the information that I have given in the question is not sufficient to tell you what values of alpha 1 and alpha 2 you have to choose. You need some additional information to actually, like basically I have 2 equations and 4 unknowns, so I will not be able to solve it directly. I need 2 more additional equations. So you need more information to actually get values for them, which is something that we don't have, hence you are saying it as trial and error. Okay. I'm slightly confused about the difference between Hessian and Jacobian. Okay. So Hessian matrix, okay. Maybe you got a little confused because both are now matrices. So if you see, it is slightly simple. If my function f is a scalar, when I have done grad f is going to be a vector, and by Hessian what we do is del square f, right? So we are doing gradient of a vector with respect to another vector, so this is going to be a matrix. So this is your Hessian. In this particular question, what I have done is I have taken my f itself as a vector, so f is directly a vector, then grad f is going to be a matrix directly. But still this is going to have, the matrix is going to be something like del f del x, or f is basically say f1 and f2 if I denoted it this way. So this is going to be del f1 del x, del f2 del x, del f2 del y, sorry, del f1 del y and del f2 del y. This is my Jacobian. Hessian is where you have second order derivative. So you have del square f1, like it's going to be same everywhere, del x square. F is going to be same, f is just a scalar, del x del y. There is no f1 and f2 in Hessian, del y del x and del y square. This Jacobian here can be a scalar, can be a matrix, can be a vector, it can be anything, depending on what your f and your variables are. If you have both your function and variable as scalars, then your Jacobian is going to be a scalar. If function is a scalar and your variable is a vector, then Jacobian is going to be a vector. If both are vectors, then it is going to be a matrix. Hessian is also similar. So if you have function as a scalar and it's like basically your variable and you have your objective function, and from there if you calculate Jacobian and Hessian. So if this is a scalar, this is a scalar, both of them are going to be scalar. If this is a vector and this is a scalar, Jacobian is going to be a vector, Hessian is going to be a matrix. So maybe this, if you answer, then I will understand that you understood this correctly. So what do you think will happen for the Hessian here? What is it going to be? Yeah, I will come to your question. In the above example, need some information. Yes, we need some information, but that information cannot be provided by whoever is modeling. That has to come from the end user. So in the case of say a manufacturing plant, that additional information should be given by whoever is whoever is taking care of that particular plant itself, not the one who is making this model. It is subjective. It is kind of a subjective thing that comes from, that is what you call an experience or something, someone who has to tell. Okay, what do you think this will be? So if I have a vector variable and a vector function, so okay, before this actually going, so is it clear that you understood the difference between Hessian and Jacobian? Jacobian is just a singular first order derivative, Hessian is a second order derivative. H should still be a matrix in the last case, but this matrix is going to be, I'm not sure if you have come across 3D matrices, but this is going to be a little more complicated. Like, yeah, it's going to be a little more tricky. It's going to be a 3D matrix, fine. So, but still it's going to be a matrix or a tensor to say. Yeah, it is going to be a tensor. Let's say matrix. Okay. So in most cases of GD, we don't need to use Hessian, right? Yes. We won't be using Hessian in gradient descent mostly. But I think one of you have asked previously about pins also. Okay. Someone want to say something? Yeah. Any other questions? Any questions in the methods that we have discussed? Okay. If there are no questions, then maybe I should ask you one more question. What is this? Maybe I'll show you some code and then I just use the predefined functions and to see how these oscillations happen. Just give me a second, I'll share my screen. To those of you who are already familiar with Python, so I've just taken whatever methods that we have discussed, SAT was steepened gradient descent, and then with momentum, then with acceleration, and then ada gradient and ada delta. With all these 5 methods, the problem that we have discussed, the function that we are trying to minimize is still y equal to x square. So I'm just using TensorFlow for this. The flow that we are following here is something like this. So when you do this, what we initially have a function that y equal to x square. We write this inside this gradient tape of this particular block. What this does is it automatically calculates the gradient. How it calculates is something that we'll discuss in the next week when backpropagation comes. But for now, assume that if I use this function, it will actually give me for now. You can just take it for like. Take my word that if I use this particular function gradient of, it calculates the gradient of y with respect to x and directly gives me the value. So you don't have to worry how it does it, but it will give me those values. And this optimizer function will apply the gradients to that. How does it apply? Like it is based on whatever I have shown before. So xn plus 1 is actually given delta xn. So it applies the step, it calculates the step depending on your gradient and the current value of x. You give both of these. In addition, you also have some parameters. Say in case of steepest gradient descent, you have your learning rate. In case of momentum, you have momentum and learning rate. Depending on which function you choose, it will actually take those parameters and then add those values, and finally you get your new values. I'm just appending them here. So if you compare, I just tried all the methods in whatever functions are. That function is a very simple y equal to x square. So if I happen to see how it converges, so as you have mentioned rightly, like if you have a very low alpha value, that is your low learning rate, then it will actually take much larger time to converge. But if you see the momentum method, because of momentum, you can observe that just after second iteration, it kind of jumped to, like ideally it should be 0.46, but now x has been actually reduced further. It is because there is a gradient that is accumulated in the step 2. It's like in the first step, initially I don't have any momentum, but right after that I have some accumulated term in the first step itself. So the second one is close to each other. By now I have some velocity. it's like a ball that is coming down. So it picks up some velocity from wherever it has been released. So because of that velocity, now instead of coming to 0.46, it has moved even lower. So it has gone to 0.44. So compared to this, it was much faster. So eventually it will go to 0, much faster than what the steepest gradient descent would do. But by the time it reaches 0, it has enough momentum, so it won't stop there. It actually went even lower than that. So it actually went even below 0, and then it keeps on lowering to a certain point till again the gradient it will keep on lowering to till where that it has sufficient momentum, but then the momentum will keep on reducing because your gradient is in the opposite direction. So there is two opposing forces here. So gradient is trying to move you close to 0, but momentum is telling you to move away from 0. So there will be a certain point when both of these kind of cancel each other. That is when you kind of retrace again. So it's around this minus 0.2. That is when you have this reverse one dominating. So the gradient will start dominating, and then you will move in the opposite direction. So you will go to minus 0.18, minus 0.16, and then eventually you come to 0. So this is what he was speaking about. You have oscillations. So I've stopped at 20 iterations, but if you keep on iterating more, you will see that it will oscillate around 0, and eventually it will come to 0. Now if you see the same in NAG, now in the accelerated part, like what we have said is, we do not directly go to the next step. Instead, we will see what the next step is going to be one step ahead, and then take the correction accordingly. So if you see here, with the momentum method, I would have been at 0.48, but I know I should not be taking too high value, too much larger step. So what NAG does is, if you remember, recollect the equation that we have, if the gradient is still negative, you can actually take much bigger step. If gradient is turning out to be positive, then you should actually be taking much smaller step. So in this case, when you are at x equal to 0.5 in the function y equal to x square, the gradient is actually favorable. So you should be actually taking much larger step than what the momentum method does. So that's why your value, instead of 0.48, it's been even lower to 0.46. The same keeps going on. You can observe this here, that whatever step size we are taking there is versus, if you compare the momentum versus the NAG1, you will see that the step sizes will be much bigger in NAG because you are in the favorable direction. So you will actually reach much faster here. But then, like as we discussed, the oscillations should actually be reduced in NAG because you are having one step look ahead. So that is what you observe here. So you have been you went to negative values, but then you kind of quickly came back to 0, which did not happen in the momentum method. So even here you are still minus 0.13, but when you implemented with NAG, it kind of came to minus 0.09 quite quickly than the momentum method. So this is going to accelerate, this is going to converge faster than your pure momentum method. Now coming to ADA grade and ADA delta, like as we discussed, so what we are doing is you are actually taking all these accumulated gradients and then you are adding them in the denominator, so that as your iteration numbers increase, you can actually the particular learning rate will actually reduce, so you will smoothly converge to your solution. That is what that is happened over here. So it will smoothly converge to 0. So in this particular case, it kind of worked better than your steepest gradient descent, but it might or might not be. Like, it is a single variable problem, so you might not see much of the advantage, but when you have multiple variables, then you can actually see it much better. And in ADA delta, the difference, as we have said, instead of just taking sum, you are actually taking weighted average, or to say an average one. So you will take all the previous one to be same, or you can use some exponentially weight factor, so that whatever are the recent weights, you give more weightage to it, and whatever are the very older weights, you kind of give them lesser weightage. So that is when you have an exponential kind of one. Depending on your weightage you have chosen, it will actually, in this particular scenario, it kind of didn't work well, but it usually performs better in some scenarios. So are there any queries? Like, this is what we have discussed, so I just gave some numbers here so that you can understand this a little better. So any queries in this? No queries? Okay.
Just one addition here. So in practical situations, you have to use all of these as a list. Some trivial situation, if something works, something doesn't work, and there's we can interpret after post-op with it. We can interpret after model being trained. So what will work? It's hit and trial method. Eventually, we also do a lot of iterate trial. Depends on data.
Yeah, like as you said, so it's not a one-time, like it's not a one solution fits all kind of thing. So you have to try with different models, and
Correct.
depending on your particular application, one of these can actually work much better than the other ones.
Price.
Yeah. If you have any other questions, then we can discuss them. If not, then we'll see the next problem. So this is the second problem that we have discussed, where you have your objective function is a vector instead of a scalar. So like as I have said, this is just some bit of a manipulation that I have done here, but then the only difference between the previous one and here, previously I was using the gradient function. If you happen to see here, I am using a gradient function. The gradient function will always return me a vector, but as we have discussed, it is if you have your original function itself as a vector, then your gradient has to be a matrix instead of being a vector. So I should be using Jacobian. The function name is Jacobian that you should be using. So once I have the Jacobian, I can just multiply with whatever alpha rates I have, and then from there I'll update these values. So if you have to observe these values, this is x and this is y, so your x is kind of a constant one and your y keeps on decreasing. So for the particular function that we have chosen, x and my vector function is minus x and x square plus y square. So your objective is like y should actually go to 0. That is what is happening here. So I've just stopped after 10 iterations, but if you keep on doing it, it will actually eventually go to 0. And your x is something that has kind of stopped. This is because of the values of alpha I have chosen. In this particular scenario, I have taken both of them to be equal. Now you can change these alpha values and see how it actually comes out. I'll upload these in the drive folder that is shared with you, so you can try out with different values and see how it actually converges. But as I mentioned, these alpha values that you chose here is something that should come from, not from you, but from the, it is something that needs to be provided in addition to whatever is already provided to you. So you cannot directly come up with some right value or optimal value for it. I hope this is clear. There are no queries, right? Yeah. So we have around 15 minutes left for us now, so I'll keep the forum open for discussion. If you have any other queries, then we can discuss them. Yeah, the last 15 minutes I'll reserve for any discussions or any other questions that you have, technical or non-technical. If you do not have any queries, then yep, you can like feel free to leave the session. So I'm not going to cover anything additional from here on. Thank you.
It seems a lot of work, Durga. I think so.
Yeah, sorry.
It seems a lot of work to us, like really difficult to sit even.
Sorry. This session is actually being recorded. So
Yeah. No, it's fine.
I hope the remaining, whoever is left still in the meeting, do you have any other queries? Even something that you want to discuss or something? Even Nitin is here. So some of you are asking on some books. So he shared a book on the forum.
Yeah. So I have shared a book called Fundamental of Deep Learning. We have found this book in the last year only. Professor wanted to write the similar book, followed this curriculum of this course, but we almost found a very similar book. That books is very, very well aligned to our course only. So then Professor dropped the idea and we are using this book. And one of the best book we ever seen in deep learning without any flaws and freely available.
Can you have it's freely available?
Okay, I have posted on the, okay, let me do the link also. Just give me a second. Something which I
Posted in announcements, yes. So other than books to refer, you have any other queries? So last time I heard a query asking on the books, and any other ones? And by the way, I just want to take you all a little time to, there is actually a feedback form that is being shared with you. So please do share the feedback on the live sessions as well, so that if you want something, you can directly tell me now, so we can incorporate in the upcoming session. So do you want more problems or coding, or which kind of way you want it? If you let me know, then we can align right now. Share the feedback form as well, so the NPTEL also does share it with us.
I have shared the link on the forum. Oh, sorry, the chat
Chat
window.
box.
Okay, Durga, I'm also leaving. Thank you so much.
Thank you for joining. So whoever is remaining, you have any questions? No? Okay then. Thank you. So I'll keep the forum open for another 5 minutes. So if you have something to discuss, you can just ask me. If there are no queries, then maybe I'll end the session. Thank you all for joining. We'll have a meet in the next week. I'll end the call for everyone then.